Lecture 12, Cautions in Analyzing Associations. We are going to talk about reasons to be careful when drawing conclusions from specifically linear regression. This is a really important point because linear regression is an extremely important tool in statistics. It is one of the most misused and overinterpreted tools. There is something extremely compelling about seeing this precise-looking linear equation with lots of decimal points that alleges to tell you the relationship between two messy things in the real world, and people regularly read too much into it. So this is about reasons to be careful, pitfalls to avoid, and subtleties that may crop up. And I want to make a point about linear regression that will be useful. I want to give you a visual image. Last time we talked about the fact that the least squares line is the one that minimizes the sum of the squares of the errors, specifically the sum of the squares of the residuals. That's a rather arcane notion. I assured you that the least squares line fit roughly your notion of the line that best fit the data, but that was not obvious. Let me give you a visual picture of what that line, how that line fits the data, which will help in the extreme cases. I want you to imagine making the line stiff, making it a stick, and then attaching your stick to each of the points with a spring that's sort of only in the vertical direction somehow, so that the point, if it's above the line, pulls it up, and if it's below the line, it pulls it down. So all of these points exert their pull on the line, and it comes to rest someplace where all those pulls balance out. That point, if the springs are defined appropriately, is the least squares line. It's where that stick will settle, being pulled on vertically by all those points. Okay, so first two cautions that you should be reasonably, or three cautions that should not come as a surprise to you because we've talked about them before. First of all, if your relationship, the relationship between your two variables is not linear, then r squared, and the least squares line are not telling you anything useful. None of them is worth doing. None of the interpretations we've talked about apply. You just shouldn't do them. So before doing any of those calculations, you should look at the scatter plot and make sure that the data is reasonably linear. Secondly, even if the data looks linear, there's no reason to think it will continue to be linear for different x values. So everything you conclude about these quantities makes sense only for x values in the range of x values for which you have data. Using your least squares line or any of those tools for x values outside that range is called extrapolating, and it predicts either something not very useful or complete nonsense. Finally, we have said before that two variables being associated does not mean that the explanatory causes the response. People frequently think this, particularly in linear regression, and because in linear regression association is referred to as correlation, typical way to say this is correlation does not imply causation. That is the text of my favorite XKCD cartoon, which you should read. But now I want to talk about outliers. You remember outliers are points far enough from the others that they require an explanation. Because we have two dimensions of data, there are multiple different kinds of outliers, essentially four different kinds of outliers. The first is outliers in the x direction. That is a point whose x value, ignoring y, is unusual, larger or smaller than the others. Below you see two examples of outliers in the x direction. Notice on the left there's a point whose x value is much larger than the others, but it still seems to follow the linear relationship. On the right there's one that does not follow the linear relationship. So that can go either way. Outliers in the x direction one should be especially careful with, and primarily for the following reason. As I said, the linear relationship only makes sense for points for which you have, for x values for which you have data. It's, I think, clear that adding that extra point does not triple the range of x values for which you have data. it only really makes sense still to look at x values for which you have a reasonable amount of data. So that least squares line is only really going to be sensible for the range of x excluding that outlier. So that's a pretty good argument for excluding the outlier. Often people will exclude outliers in the x direction if there's a good reason to think that it is a separate situation, that it's got different things going on causing the outlier in the x direction, and only applying their conclusions to that narrower range. Outliers in the y direction are those where the y value is unusual and the x value is not, and these tend to be less of a cause for concern. Sometimes, as in the first example, where I recycled the same example because that point's both an outlier in the x direction and in the y direction, on the right-hand side I have 3 points that have very large y values, large enough you could probably call them outliers in the y direction, and 2 points that have very small y values, probably you could call them outliers in the y direction. It's not clear that those points upset anything about the linear relationship. So an outlier in the y direction, one should notice, one should think about why it's an outlier, but that does not tend to disrupt linear regression. Finally, we have regression outliers. A regression outlier is defined as a point which has an unusually large residual. Remember what the residual is. The residual is the y value minus the predicted y value. Visually, on the scatter plot, this is a very important point, the residual is the vertical distance from the point to the least squares line. So on the left, you have this red dot labeled outlier, and you can see it's way below the point on the line directly above it. On the right-hand side, right in the middle of the graph, you have an outlier whose y value is very high, and it's way above the least squares line, which is below it around the middle of the graph. So those are both regression outliers. Here's what a regression outlier is. It's a point for which the linear relationship that seems to apply to the other points does not apply. It is something is pushing it far from that underlying relationship, and that something is the interesting story you should be identifying in that instance. You can see from this graph that the outlier on the left is having a dramatic effect on the least squares line. If you removed it and eyeballed where the least squares line should be, it would be nowhere near the line we've drawn. On the right, it doesn't seem to have had much of an effect at all. If you removed it and eyeballed where the least squares line should be, it would be pretty close to that line. That distinction is very important, and so we use two terms. So within regression outliers, a regression outlier can either be non-influential or influential. And the definition is very mechanical. You can tell just based on its x value. A non-influential outlier is a regression outlier whose x value is reasonably close to the x mean. So on the left, the circled point is well above the least squares line, high enough above you could argue that it is a regression outlier, but its x value is pretty average. It's around 20 or 25, which looks pretty close to the average. So it is a non-influential outlier. Again, if you erased that point and eyeballed where the least squares line would be, it's not clear it'd be any different. On the right, the point in the middle way up high is clearly a regression outlier. It's got a huge residual, but again, its x value, which is around 0.5 or a little bit less, is just about in the middle, and again, that makes it a non-influential outlier, and you can see, if you deleted it, the effect on the least squares line would be pretty small, just based on eyeballing it. On the other hand, an influential outlier is a regression outlier whose x value is far from the mean, either far above or far below. So here's on the left is an example. The red dot labeled outlier has a huge residual, huge negative residual, and its x value, which is almost 8, is well above the mean, which is somewhere around 4. And sure enough, you can see that the least squares line with it is nowhere near the least squares line without it. Same thing happens in the second picture, the blood selenium graph on the right. Why is that? So imagine attaching that spring to the point, and if it's a regression outlier, to the line far away. That point is going to pull hard on the line. If it's a non-influential outlier, if its x position is average, it's going to pull up or down on that line a little bit, and now most of the points will be above or below and will be pulling in the opposite direction. So lots and lots of points pulling a little bit balances out one point pulling a lot. So the overall effect of a non-influential outlier is it pulls the line towards it a little bit. In an influential outlier, it's more complicated. It's pulling on one side of the line, which causes it to twist. As it twists, some points will be pulling against it, but the points in the middle really won't be. They won't be bothered by the twist. So it's one point pulling very hard against a small number of points pulling less hard. So to balance each other out, it manages to pull the line quite a bit towards it. The spring picture, I hope, gives you an image of the line twisting quite a bit. I'm going to give you an example that occurred in my survey one semester, so I'll give you a little bit of a background. We're interested in the relationship between high school GPA and college GPA. It is obvious that you should think of high school GPA as the explanatory variable and college as the response, because high school GPA happens first. If there's going to be any influencing, the earlier thing has clearly got to influence the later thing, not the other way around. So, in the beginning of the semester, as I did with you all, I asked everyone their high school GPA and their college GPA, but I accidentally marked one value wrong, and I got an outlier. And I want to show you this. First, I'm going to show it to you without the outlier. So the x-axis is high school GPA, the y-axis is college GPA, and in the upper right-hand corner you see the least squares line, y equals 0.3732x plus 1.8792, and r squared is 0.07408. Let's practice interpreting those. That slope, approximately 0.37, tells you each time the high school GPA goes up by 1, you should expect college GPA to go up by about 0.37. In other words, if I had a B average in high school and you had a C average in high school, so I was 1 point GPA higher than you, I would expect in college that I would probably have a higher GPA than you. How much higher? About 1/3 of a point. If you had a C+, I'd have a B-. Not surprisingly, higher GPAs in high school go along with higher GPAs in college, but less, right? Because other things affect it besides high school GPA. The number 1.88, the y-intercept, should be telling you that if your high school GPA were 0, you'd expect on average to have a college GPA of 1.88, but in this case, that interpretation doesn't make sense because we have no data that goes anywhere near x equals 0. Our smallest data point looks like it was 2.0, and most of the data is 2.8 or higher. So the y-intercept interpretation in this case doesn't apply. Finally, our r squared was 0.07, which is a 7% r squared, which would be a means that 7% of the variation in y is explained by its linear relationship with x. The other 93% is explained by other things that affect college GPA but not high school GPA. That's a very weak relationship. And usually that is a weak relationship. That may surprise you, has to do with things about the Fairfield admissions process, sorting by majors. In any case, you would expect, seeing this line in r squared, to see a data with a clear positive relationship. The slope is positive 0.37, but very weak, so data loosely scattered around a line of positive slope. Instead, we're looking at what looks like data tightly scattered around an almost horizontal line. The reason for that is the scale of my picture. And you should always notice the scale in any graph, especially a scatter plot, the scale dramatically influences what it looks like. You can see here my x scale is pretty reasonable, from 1.8 to a little over 4, but my y scale is ridiculous. It goes from 0 to 45. Because the y values range from 1 to 4, everything is crowded in the bottom, and it makes the positive association look almost horizontal. It makes all the points look very close to the least squares line because we have a silly y scale. So one takeaway here is the picture is dramatically affected by the scale. You should make sure that you're looking at a reasonable scale before you try and draw too much conclusions from the picture. Why did I draw such a silly scale? Because I wanted to leave room for my outlier. What was my outlier? Somebody typed in a college GPA of 4.0 and I left off the decimal point. I am at one point with a GPA of 40. And here it is. There you see somebody who had a high school GPA of about 4, or maybe a little less, and a college GPA of 40. That is clearly a regression outlier. That point lies way above the least squares line. It is an influential outlier because its x value, which is almost 4, is well above the mean. What effect does it have on the least squares line? Well, the slope, which was 0.37, is now 3.1. It is almost 10 times as big. The y-intercept, which was 1.8, is now negative 6.8. Somebody with a high school GPA of 0, this would claim, would have a college GPA of almost -7. And r squared went down, although interestingly not by much. This is a ridiculous line now. It has nothing to do with the relationship between these 2 points. It's been completely overwhelmed by the effect of this single mistake. On the other hand, here's the data back again. If I had made the mistake with some point whose x value was more middling, here I have a x value of around 3.4 and a y value of 40. So now the x value is close to the mean. You can see the line didn't really move much. The slope changed from 3.7 something to 3.8 something, just went up slightly. The y-intercept went up from 1.7 to 2.5, so definitely the line lifted a bit, a modest amount, but not huge. Notice r squared went way down. Why? Because we've added a huge amount of variation in y that's not explained by x. The whole residual of that point is huge, and obviously is not explained by x. So, influential outliers screw everything up. Non-influential outliers should be approached with caution, but don't necessarily ruin your conclusions. In any case, every regression outlier has a story. It's a story that explains why it's not fitting the relationship of the other data, and it's one you should try and figure out. I want to briefly tell you my favorite example from an old textbook we used, which had data from some lake in Sweden where people fished. For each fish, they wrote down its length and its width. You might expect that those would have a positive relationship. Why? Because if one fish is twice as long as the other, it's probably going to be twice as wide as well, right? They have similar shapes. And that's indeed what you saw. You saw a nice, tight linear relationship, a strong, positive linear relationship between length and width. But you saw one outlier, one point, which had a much bigger y value than you would expect. Here we're using length as the x value and width as the y value for no particular reason. So that's a point whose width was much more than you'd expect knowing their length. What's that? That's a fat fish. A fish that's too wide for its length. Way too wide for its length. What's the reason? Well, a little footnote in the book told you this was a fish who had just swallowed another fish right before he was caught. So his belly was distended. He was way wider than usual, he or she. That is what you should think of when you think of a regression outlier. Okay, so to summarize, here's what you should know, and pretty much negative things. You should know not to draw conclusions for x values outside the range for which you have data, and you should know not to infer causation simply from a correlation. And once we've worked on this a bit, you should be able to recognize the different types of outliers: x direction, y direction, regression outliers, and influential outliers. A point can be more than one of these things. And you should understand their different effects on the least squares line.